So last class we talked about solving three-variable systems by substitution, and today we're going to learn how to solve these three-variable systems by elimination. Most of the time students like elimination better, they go a little bit faster, and there's a little less algebra, so I think everyone's going to be a little bit happier. The first step to solving by elimination is to eliminate one variable to obtain a linear system in two variables. Okay, we already want to create that new system with two variables. The second step is to solve this new system for both of its variables. Okay, so now that we've created a new system, we want to solve that system for both of its variables. Step 3 is that we want to substitute those values into one of the original equations substitute it into one of the original equations and solve for the remaining variable. Okay. Once we've done that, it'll be just like the last step of substitution, where we take both of the variables we've solved for already and plug it back into one of the beginning ones to get the last variable. Now a note to make is that still, if we get 0 equal to 1, that would be that there is no solution. So if your variables drop out and you're left with something that's not true, like 0 equals 1, you would say that the system has no solution. If your variables drop out and you're left with something that's true, like 0 equals 0, that still means that there are infinitely many solutions. Okay, so your options are still one solution, which is our ordered triple, no solutions if your variables drop out and you're left with something that's not true, or infinitely many solutions. Now we're going to do 4 examples in your notes today. The first 2 are kind of long and the next 2 go pretty quick, and you'll see why. Here's our first example. It is the system 4x plus 2y plus 3z equal to 12, 16x plus 5z equal to negative 6, 6x minus y plus 4z equal to negative 3. First thing I want to do when I'm solving these systems by elimination is just number the systems 1, 2, and 3. That way we can keep track of what we're doing to what in each step. Step 1 says I want to multiply or divide by numbers so that I can eliminate some variables. So the first thing I want to do is I want to multiply 2 times our third equation and add it to 1. If you notice, my third equation has a y variable of negative 1 coefficient. My first equation has positive 2. So if I multiply 2 times this entire third equation, I'll have positive 2y in equation 1 and negative 2y in equation 3, and that's what I want to be able to eliminate. So we go ahead and do that. So here's my third equation multiplied by 2. I'd get 12x minus 2y plus 8z equal to negative 6. That's 2 times that third equation. And I'm going to add it to that first equation. So I have 4x plus 2y plus 3z equal to 12. When I add these two equations, 12x plus 4x is equal to 16x. The y's eliminate, and 8z plus 3z is 11z. That's equal to 6. Okay, I currently have 2 equations with 2 unknowns. I have created my new system. Here's my new system. It is equations 2 and what we'll call 4. Okay, it's the system 16x plus 5z equal to negative 6, and 16x plus 11z equal to 6. Now if I'm solving the second system by elimination, we notice that this second equation only needs to be multiplied by negative 1 so that this x variables will cancel. So if we rewrite this system, we have 16x plus 5z equal to negative 6. That one is unchanged. Multiply everything in the second equation by negative 1. I'd have negative 16x minus 11z equal to negative 6. Okay, if I add these two equations, my x variables will eliminate, and I'll be left with negative 6z equal to negative 12. Solving for z, I get that z is equal to 2, and I have my first part of a three-part solution. Now, since I have the first part of that answer, make some room for myself here, I have the first part of my answer in my new system. To find the second variable in my new system, all I have to do is substitute this solution back into either one of these original equations in my new system to solve for x. So let's do the top one. We don't know what x is, so we still leave 16x, but we do know what z stands for. Z is 2, so I can substitute that in. I'm left with 16x plus 10 equal to negative 6. Solving for x, 16x equal to negative 16, and then x equal to negative 1. Here's my second part of my three-part solution in my ordered triple. So far, I know that x is equal to negative 1 and that z is equal to 2. I also know that I have still these original equations sitting at the top of my page, 4x plus 2y plus 3z equal to 12. Okay, this was equation 1 from my beginning. I don't need to bother writing down the other ones because I can solve for x, the only variable I'm missing, just with this top one. Okay, all I do is substitute in for what I already know. I know that x equals to negative 1. We don't know y yet, that's what we're solving for. And z is equal to 2. Okay, multiply these out. We have negative 4 plus 2y plus 6 equal to 12. 2y plus 2 equal to 12. 2y equal to 10. And that y is equal to 5. Okay, this is the last part of my three-part solution. And the ordered triple that solves the system is negative 1, 5, 2. My next example is the system 8x minus 6y plus 2z equal to negative 20, negative 3x plus 6y minus 15z equal to 51, and 2x plus y plus 3z equal to 0. The first thing I want to look for when I'm solving for elimination is variables that have the same coefficient or that are positive and negative of each other. If you notice, right here, equations numbers 1 and 2 have positive 6y and negative 6y. That's a good sign. We don't have to multiply these equations by anything to eliminate a variable. So let's go ahead and eliminate this one. We have 8x minus 6y plus 2z equal to negative 20, and minus 3x plus 6y minus 15z equal to 51. If I add these together, I would be left with 5x and minus 13z equal to 31. Okay, that's half of my new system. I also need to eliminate y from the other equations. Okay, the other two I can combine together. Since I already did 1 and 2, means I can combine 1 and 3 or 2 and 3. Now, if you notice, again, this is already minus 6y. This one is already positive, which means that I just need to multiply this entire equation by 6 so that this says plus 6y. Okay, if we multiply 6 times number 3 and then add it to number 1, we're going to get our new system. So let's multiply 6 times this third equation. I'd be left with 12x plus 6y plus 18z equal to 0. And my first equation is still 8x minus 6y plus 2z equal to negative 20. Okay, I add these two equations together, I get 20x, the y's eliminate, plus 20z equal to negative 20. Okay, we have our new system now. Our new system is 5x minus 13z equal to 31, and 20x plus 20z equal to negative 20. Two variables to solve for, and two equations. That's a good sign. It means I can do it. Now we want another variable to eliminate out. I don't think that 13 and 20 have very easy common multiples, but if you notice, 5 and 20 do. If I multiply 5 times 4, I'd get 20. Which means to solve a new system, what I'd like to do is multiply this entire equation by negative 4. Okay, if I multiply the entire equation by negative 4, I get the new system, minus 20x plus 52z equal to negative 124. Okay, I'm going to rewrite this equation from the right-hand side of the page underneath that equation so that I can add them together. When I add these two equations together, the x's eliminate and I'm left with 72z equal to negative 144. If I solve for z, divide by 72 on both sides, I get that z is equal to negative 2. And that's the first part of my three-part answer. Now the only thing that I know thus far is that my value of z is equal to negative 2. I need to substitute this value back into one of those new equations to solve for x. Okay, my new equation is minus 20x plus 52z equal to negative 124. Okay, I just substitute it right on in. Negative 20x plus 52 times negative 2 equal to negative 124. 52 times negative 2 is negative 104. If I add 104 to both sides, I get negative 20x equal to negative 20. And therefore x is equal to 1. Here is the second part of my three-part answer. Since I have two of my variables, I know what x and z are, I can substitute them back into one of the original equations to solve for y. Here's one of my original equations. 8x minus 6y plus 2z equal to negative 20. Since I know what x is, I substitute that in. I don't know y, but I know z. So this is 8 minus 6y minus 4 equal to negative 20, or negative 6y equal to negative 24, which means that y is equal to 4. And now I have all three parts of my three-part answer, and the ordered triple that solves this system is 1, 4, negative 2. Our third example today is the system x minus 2y plus z equal to negative 11, and 3x plus 2y minus z equal to 7, and negative x plus 2y plus 4z equal to negative 9. So the first thing we're going to do is look for what we all want to eliminate first. You notice that equation 1 and equation 2 and equation 3 are related by their y's. Equation 1 says minus 2y, and both of the other two equations say plus 2y. Okay, that's an indicator that we want to eliminate our y's, and that we're not going to have to multiply by any coefficient because these are already matching. So first, as we always do, let's number our equations, 1, 2, and 3. And the first thing I want to do is add 1 to 2. When I add equation 1 to 2, I'm adding x minus 2y plus z equal to negative 11 to 3x plus 2y minus z equal to 7. When we do this, we get 4x, my y's canceling, and my z's canceling, which means that 4x is equal to negative 4, or that x is equal to negative 1. And I already have one of the solutions to my to the ordered triple that solves my system. Alright, that seems pretty cool. Let's keep going. Okay, if we add 1 to 3, the other two that have that matching coefficient, I'd be adding x minus 2y plus z equal to negative 11 to negative x plus 2y plus 4z equal to negative 9. When I add these, my x's will cancel, my y's will cancel, and I'll be left with 5z equal to negative 20, and solve for z so that z is equal to negative 4. Here's the second part of my three-part answer. All that's left to do is to substitute these values into either 1, 2, or 3. It doesn't matter which one I substitute into, it will give me the correct answer. I'm going to choose the top one out of habit. Okay, we know that x is negative 1. We don't know y, but we do know that z is negative 4. And all of that together should equal negative 11. Okay, I get that negative 2y minus 5 is equal to negative 11. Negative 2y is equal to negative 6. And that y is equal to 3. Here's the third part of my three-part answer. And the ordered triple that solves this system is negative 1, 3, negative 4. So the key here is to look for easy eliminations first. If you notice that this is sitting here, and that this is sitting here, and that this is sitting here, you know that your system will eliminate very quickly, which will lend you to finding your answer in only one slide rather than two. Okay, so always look for these easy eliminations first before you start multiplying your systems. Okay, our last example of the day is the system x plus y plus z equal to 2, 5x plus 5y plus 5z equal to 3, and 4x plus y minus 3z equal to negative 6. So there are no straightforward hints here, so we just have to make one work. So first thing I want to do, after I number my equations, is I think I'm going to multiply 5 times the first equation, add it to the second. Okay, if I multiply, negative 5 times the first one, I would get negative 5x and then 5x, which is good. I'll go ahead and do that. Negative 5 times the entire first equation would give me negative 5x minus 5y minus 5z equal to negative 10. Okay, and I want to add that to my second equation, like I said. 5x plus 5y plus 5z equal to 3. Now when I add these equations, well, the x's cancel, the y's cancel, and the z's cancel, which means I'm left with the phrase 0 equal to negative 7. Now this is not true, and immediately I can stop and I can say that this system has no solution. Easy as that.